गणनायकाय गणदैवताय गणाध्यक्षाय धीमहि गुणशरीराय गुणमण्डिताय गुणेशानाय धीमहि गुणातीताय गुणाधीशाय गुणप्रविष्टाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचानाय श्रीगणेशाय धीमहि एकदन्ताय वक्रतुण्डाय गौरीतनयाय धीमहि गजेशानाय भालचन्द्राय श्रीगणेशाय धीमहि.
About the college, Vasreddy Venkatadri Institute of Technology was established in the year 2007 under Social Educational Trust in Nambu village, Pedakakani Mandal of Guntur district by Sri Vasreddy Vidyasagar sir. VVIT has self-contained infrastructure located amidst the lush greenery of paddy and maize fields of Nambur located strategically between Guntur and Vijayawada, away from the hustle and bustle of the city life. VVIT is ISO 9001 2008 certified, NAC accredited with A grade. All UG branches are accredited by NBA and is permanently affiliated to JNTU Kakinada. In a short span of 15 years, with an annual intake capacity of 1,620 students in BTech and 72 students in MTech programs, today the institution has more than 6,000 students, 345 teaching staff, and 225 non-teaching staff, striving to fulfill the vision of the institute. VVIT has emerged as one of the top 10 engineering colleges from the 200 engineering colleges affiliated to JNTU Kakinada. VVIT is an official skill development center for APSSDC and is recognized as Center for Excellence by Science in association with APSSDC. About the Department of Electrical Engineering. Electrical Engineering department was established in the year 2007. Its graduates are serving the society since 2011 and have been making tremendous impact to the well-being and development of the country. The department has been so structured in terms of experienced staff and excellent laboratory facilities. The department is offering BTech with an intake of 180. The department is accredited by National Board of Accreditation for 3 years from 2017. The department provides ample opportunities to students to work on mini projects, develop communication skills, explore internship opportunities in industry, and take active participation in national and international design concepts. The faculty members of the department extend the guidance for research scholars to publish their work in the reputed index journals. Department vision is to nurture young and fresh minds into disciplined and globally competent technocrats with ethical values to excel in the arena of electrical and electronics engineering, leading to sustainable development of society. Objective of the Faculty Development Program. This training program will provide complete knowledge on battery tech which makes EVs more affordable and accessible than petrol, diesel, or gas cars, thus boosting their demands. The rapid production technology will make EVs available for the masses by ensuring supply can keep up with rising demand. Theme of the FDP. The Faculty Development Program focuses on recent innovation and technological developments in the emerging areas of electrical engineering to solve real life problems occurring in different domains. Now, I request Dr. A.V. Naresh Babu sir, HOD of EEE Department of VVIT, to address the meet.
Thank you, Chandrika. I am audible? Thanks, sir.
Yes, sir. Yes, sir.
Right. Honorable Chairman, sir, Vasireddy Vidya Sekhar garu, esteemed Secretary, sir, Badri Prasad garu, admire Joint Secretary, sir, M. Sri Krishna garu, respected Principal, sir, Dr. Y. Mallikarjun Reddy garu, Dean of Academics, Dr. Giribabu garu, Dean of Administration, Dr. N. Kumar Swami garu, Dean of Freshman and Training and Placement, Dr. M. V. Agram garu, Coordinator of the FDP, Dr. Bhakta Singh garu, today's chief guest and keynote speaker, Dr.O.Chandra sir, Professor and HOD and New Delhi, heads of various departments, my colleagues from VVIT and other colleges. Good morning to one and all. It gives me an immense pleasure to welcome you all for the 1 week online FDP on electric vehicles, technological advancements and trends organized by the EEE Department of VVIT from 28th to 25th February 2023. Let me mention a quote of great personality, Dr. APJ Abdul Kalam Garu, which is associated with FDP. Success is a vehicle which moves on a wheel named hard work. But the journey is impossible without fuel named self-confidence. Success, hard work, self-confidence are associated with vehicle wheel fuel. Coming to the FDP, as we know, the electric vehicle plays an important role in the transportation sector because of zero pollution. This FDP will provide the knowledge on e-mobility, technical advancements and trends of electric vehicles, which is necessary for realizing smart cities vision of India. All the sessions will be delivered by the senior and eminent speakers from previous institutions like IITs and NITs. I sincerely hope that the discussions and the information shared in the FDP by the resource persons can extremely useful for each and everyone. I would like to thank all the speakers for accepting our invitation in spite of their busy schedule. Also, I take this opportunity to express my sincere thanks to our Honorable Chairman, Sir, Vasireddy Vidya Sekhar Garu, Secretary, Sir, Badri Prasad Garu, Joint Secretary, Sri Krishna Garu, and Principal, Sir, Dr. Y. Mallikarjun Reddy Garu, Dean of Academic, Dr. Giribabu Garu, the EEE Department staff for their excellent support and valuable suggestions and constant encouragement for organizing this FDP. At the outset, I especially congratulate the coordinator of the FDP, Dr. Singh Garu, for his continuous effort to organize this FDP. Finally, I am very much thankful to all the participants for registering this FDP. I wish you all a 1 week interesting and useful sessions. Happy learning. Thank you, one and all.
Thank you, sir. Now, I request Dr. N. Kumaraswamy sir, Dean of Administration of VVIT, to address the meet. I request Dr. K. Giribabu sir, Dean of Academics of VVIT, to address the meet.
Okay, am I audible? Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Namaste and good morning, everybody. First of all, my congratulations and best wishes to the Electrical and Electronics Engineering Department for planning and materializing this 1 week online faculty development program on electric vehicles, technological advancements and trends from 20th to 25th of this month for all aspiring electrical and electronics engineers. My warm welcome to all the participants who registered and joined from various institutions working as faculty and research scholars. I would also like to extend my sincere gratitude to all the learned keynote speakers and expert resource persons for their kind consent to share their valuable knowledge. I wish this FDP would cater all the participants in satisfying the quest for exploring electric vehicles with the trending technological advancements from the other domains, especially from cutting edge software. The Department of EEE of VVIT, which is organizing this FDP, has significant achievements in teaching learning, training, placements, innovation, entrepreneurship, and research and development in these years. On behalf of VVIT, I thank and honor the acceptance, readiness, and virtual presence of the distinguished keynote speakers, scholarly resource persons who are going to share their invaluable knowledge acquired through their relentless hard work. I present a bow of respect to the chief patron for this FDP, our chairman of VIVA VVIT institutions, Sri Vasiredi Vidyasagar Garu, a silent visionary with a missionary zeal who supports us always to keep up any challenging step forward into the realization of our VVIT's vision. I also thank our principal, Dr. Y. Mallikarjun Reddy Garu, Secretary Badri Prasad Garu, for organizing this FDP. I am proud to say VVIT always stands ahead in supporting every activity that will motivate true engineering educators and researchers. I once again convey my best wishes to all the wise participants of this FDP who are all set on this virtual platform, ready to imbibe every key point of this program. We wish this FDP will achieve its objectives in a fruitful manner. Thank you, one and all. Thank you.
Thank you, sir. I request Dr. Y. Mallikarjun Reddy, sir, Principal of VVIT, to address the meeting.
Okay, thank you, sir. Respected today's chief guest and keynote speaker, Dr.O.Chandra Sekhar from NIT Delhi and the Professor Electrical Department. Sir, good morning, sir.
Good morning, sir. Good morning, sir.
So the guests and the faculty members of EEE department and management of Vasiredi Venkatadri Institute of Technology and the guests from different engineering colleges, the participants who are participating in this technology, warm welcome to all for a one-day online workshop FDP program on electrical vehicles, technological advancements and trends. And this will be conducted for 1 week. And the invited guests are from the experts from the different NITs and IITs, right? And then they will give their valuable information and the advanced technology developments on this area. So the participants will gain a lot of experience and they know about how the electric vehicles can run with the electrical motor and transmission system, right? With battery, right? So there is a lot of technological improvements required in the recent trends. So this year, so the battery, mainly that is used with lithium-ion battery, right? So at present, there is a lot of research is required, right, on lithium-ion battery to reduce the size. So there is a lot of material innovation in the material and how they are going to use and to improve the charging time, right? And discharging time and charging and discharging time and reduce the size of the battery and to improve the efficiency, right? And also adding with the electric vehicles with artificial intelligence, machine learning and deep learning technologies to utilize the efficiency of the powertrain of the system, of the total system. So as you made out,
తొందరగా స్టార్ట్ చేయండి వాటిని స్టార్ట్ చేసి స్టాండ్ బై లో పెట్టండి కొత్త బండ్లన్నీ స్టార్ట్ చేయండి తొందరగా స్టార్ట్ చేయండి వాటిని రాజేష్ స్టాండ్ బై లో పెట్టండి.
Hello? Hello? Is it audible?
Audible,
Thank
sir.
you.
Audible, sir. Continue, sir.
Okay, see, artificial intelligence, machine learning, and deep learning technologies will be used efficiently on the powertrain system, right? Such that the utilization of non-renewable energies, right, and renewable energy, right, that is coming from the different sources that can be utilized to power the batteries and to improve the efficiency, that is the range of the range and size of the batteries and the use of the particular aerodynamic, right, for the vehicles is also very, very important. So therefore there is a lot of the technology advancements are required in the electrical vehicles in the electrical and electronics domain, right? So there are so the changes will be can be discussed on this platform, and we can have the one-to-one interaction, or we can have to the presentations, right, with the recent technologies and the researches that is going on this technology, right, will be discussed on this platform. So therefore all the participants can utilize this opportunity, right, and they can improve their technologies and research activities. Thereby, they can present a good papers and research papers in that. Right. So once again, I welcome all the participants, right, to this one day online work, 1 week online workshop, FDP and electric vehicles technology advancement centers. So I thank management and uh, the Department of EEE for conducting this excellent program. So thank you, sir.
Thank you, sir. I request Dr. O. Chandra, sir, HOD of EEE Department of NIT Delhi, to address the meeting.
Good morning to all of you. Respected
Good morning,
principal, respected principal, Dr. Professor Mallikarjun sir, and respected Dean Academics, Girbhav sir, and principal, head of the Department of VVIT Electrical Engineering Department, Dr. Naresh Kumar sir, and the program coordinator, today's program coordinator, the directly and indirectly those who are involved in this program. I welcome all for this 5-day program. So my role is I have to give. I will by this presentation. By the end of this presentation, you will be able to know that what are the advances in electrical engineering, especially for electrical drive application, with the special motors. What are the special motors? How we need to control of electric drives, and what is the electrical vehicle scenario in India, and also the USA, Norway, and China. So these are the 4 countries, especially they are very good in developing and utilizing these hybrid electric vehicles and also battery driven electric vehicles. So these things I will highlight, and what are the changes we required for electrical engineer. It should be also demanding for all electrical engineering students as well as faculty to gain the knowledge with respect to special electric motors. We already learned the conventional motors like DC motor, induction motor, and synchronous motor. But now it is already outdated. Like computer science, already they have introducing new courses in their curriculum. But electrical engineering, they are not ready to introduce the new courses. Not ready in the sense everybody is thinking about the conventional activities only, conventional courses only. But now these hybrid electric vehicle are electric vehicles are using the special motors. What are the different types of special motors and how they are useful for propulsion of electric vehicle? So these things I will address now with my presentation. And also I am very much thankful for the organizing team and also the principal and Dean Academics for giving this great opportunity. So after this inauguration, I will immediately start my presentation. Thank you for giving this opportunity. So can I continue with my presentation, or I have 1 or 2 minutes time?
Sir, 2 minutes, sir. So just we will give some general instructions to the participants, sir. So after then, we will start the in session, sir.
Okay, sir. Give the guidelines. I will definitely start the presentation. You let me know. Okay.
Okay, sir. Okay, sir. Immediately. Within 2 minutes, sir, we will complete that one, sir.
Thank you, sir. Now I request convener, sir, of FDP to give general instructions.
Yes, good morning, everyone. First of all, thank you, the management and principal, sir, for giving the opportunity to organize FDP. That is 1 week online FDP by the Department of Electrical and Electronics Engineering in association with the Institute of Engineers, India. And I request all the participants. So first of all, greetings from the Vasudeva Venkatadri Institute of Technology. And we express our gratitude to you for showing interest and taking part in 1 week national level online faculty development program. So on electric vehicle technological advancements and trends. And this will be continue. This will be continue from today to this Saturday, that is 25th of February 2023. So I request all of you, so kindly follow these instructions. So while the sessions are going on and before the session and after the session. And the first thing is, so every day the participants need to visit our WhatsApp group for accessing online session through the link. And second one, every day there will be the 2 sessions on the topic delivered by the resource person. Forenoon session, that is in the morning, the timings from 9:30 to 11:30, and second session, that is in afternoon, from 1:30 to 3:30. And don't change your login credential from day by day. So kindly log in with the same credential for all sessions. And every day, after completion of this session, we'll give the feedback link in the WhatsApp group. So please fill the feedback link. So that filling is considered as the attendance, and 80% attendance is mandatory course. And on 25th of February 2023, that is in the last day, that is the last session, in the afternoon session, we will conduct one online test for 30 marks. It is for 1 hour, and whatever the sessions going on, from these sessions only we will give the questions. And of course, the 60% marks required to get the certificate. And if suppose if you have any clarification regarding this FTP or any online issues or any other things, feel free to contact me personally, either in contact phone or WhatsApp message. There is no issue. Yes, thank you for giving me this opportunity. Once again, thank you, Principal Sir and management, and Dean of Academics, Girbabu Sir, HOD Sir, and other department colleagues for giving me this opportunity to work as the convener for this FDP. Yes, thank you once again.
Thank you, sir. Dr.O.Chandra, sir, is currently working as an associate professor and HOD of Department of Electrical and Electronics Engineering at National Institute of Technology, Delhi. Sir has pursued BTech in the stream of Electrical and Electronics Engineering from JNTU Hyderabad and completed MTech and PhD in Power Electronics and Electric Device from JNTU Hyderabad. Sir had completed research and had 4 patents, also done one sponsored research project and one ongoing sponsored research project. There are 43 journal papers published in SCI, Scopus, and 9 conference publications. It is my privilege to invite such a noble personality, our chief guest, Dr. O. Chandrasekhar sir, to start the session.
Okay. So is it my screen is visible to everybody?
Yes, sir. Your screen is visible.
And
Sir.
I hope I am audible to all, I think.
Yes, sir.
Okay. So Thank you for your nice introduction and also for your nice gesture to give this opportunity. I once again welcome to this 5-day workshop. Uh, so on my topic today, I would like to enlighten uh, control of electrical vehicles by special electrical motors. So I think my previous speakers like principal and dean academics and head of the department, they already enlightened the need of electric drives and the importance of electric drives and utilization of electric vehicles. So these electric vehicles, how the scenario is now important in our day-to-day life. So now Ministry of all our Prime Minister is also now emphasizing about utilization of electric vehicles. So in Delhi, because especially I am staying in Delhi, so hybrid electric rickshaws are already started. If every day, if I want to go from one place to another place, if I will pay only 10 rupees, within 5 kilometers they're allowing. Just they're 2 3 hours they're charging, and then they're coming to the roads, and then for 6 hours they're running the motor without any problem. And these petrol and these natural gases and CNG machines are also not working. Just only by utilizing these electrical vehicles, they are benefiting. So what type of motors they are using, and what is the, and now maybe within 2 3 years, every all these petrol and CNG electric motors or IC these type of cars will not available, and everybody will switch to the hybrid electric vehicles or battery driven electric vehicles. We need to start. And with this approach, because last year I approached the ministry, CRB, Science and Research Engineering Board. I already filed one patent regarding the uh, sensorless control of switch reluctance motor and how this switch reluctance motor drive is suitable for hybrid electric vehicle and what type of mechanism they are using. Like especially if you talk about the Tesla motor, so why this Tesla motor is more dominating in hybrid electric vehicle technology, and also now in our India, the Tata Motors is also using developing the electric vehicles. So based on my last year project, so I got a funding project from the Ministry of Department of Science and Technology. So for plug-in hybrid electric vehicle with onboard charging capabilities. So what I am doing and what others are doing and what is the research in this particular area. So these things I would like to analyze now, and maybe few of the research scholars or few of the faculty members and few of the doctorates will also work in this particular area after my presentation, I hope. And first, my presentation will be divided into 2 3 parts. First, I'm concentrating on what are the different types of electrical motors, special motors which are used for the propulsion of electric vehicles, and the special motors, especially what are the different types of special motors which are used for the today hybrid electric vehicle technology, and what I am working on, which area I am working, and what I am my focusing on research of this electric vehicle, because everybody like power system people, they are working about the charging stations and how these microgrids will be utilized for the charging of these battery stations and battery state of no, that is also their state of battery people are working. But my area, because there is a huge forbidden in this electric vehicle, because anyway this technology has started in our India also, but in USA and also some China, they are already well versed about these systems and they are utilizing much faster than with our country. And keeping in view of that, so what type of missions we need to study? What type of motors we need to understand? Because we already familiar with the fundamentals of like electromechanical energy conversion system. So with the simple mechanical energy conversion system, electromechanical energy conversion system, we already aware about our, we are already studied our DC motors, induction motors, and synchronous motors, and all our conventional motors. So with this background, with this DC motor working principle, the same thing now again we'll go for the induction motors also. So what they have done, because before going to my actual presentation, so if you go through the Tesla data sheet of electric motor, or Nissan motors data sheet, or Tata motors what they are using. So before 2000 up to 2009, this Tesla motor, Tesla has introduced the squirrel cage induction motors for driving the electrical vehicle. So as the induction motor has a basic advantage as a that it's a rigid construction, and it can be suitable for environmental and also industrial drive and industrial purpose. This induction motor has the major advantage is it can be possible to drive an extended heating application. You know that the heat is the main problem in any motor. So in 2009, up to 2009 to 2012, the Tesla has used this motor only, three-phase induction motor with variable frequency drive for propulsion, for forward movement as well as backward movement, for both braking as well as motoring operation. As you know, once if you start the electric vehicle, you cannot stop the electric car up to 100 kilometers or up to 200 kilometers, or maybe somebody, they will in a single go, they may go for up to 400 kilometers also. As if the motor is working in the base of the car, especially the induction motor, if you run the motor above 4 hours or 5 hours, or maybe as for the user, the extended driving operations, maybe they are saying, sir, I may go up to 600 kilometers without any stop or without any charging. So now charging I am not talking, just I am talking about the motor because my area is motor only. So especially if the motor is operated with more than 4 hours, definitely the winding will be, some heat will be generated in the motor. As we know, in the squirrel cage rotor of an induction motor, it is a wound rod. It's all rotor conductors are short circuited together. So once the motor is operated up to 5 hours or 6 hours, even though if you are providing some ventilating and cooling also, then the winding will be getting as a heat. Winding will get as a heat. Once the heat is developed in that windings, the thermal loading problem will become. Thermal loading is a major problem, and the fault will occur. Because of this fault, the winding will entirely damage. Because if any one winding will be short circuited in induction motor, that is called as a shoot through fault. This is one of the important, when especially when you working for the motors for propulsion of electric vehicle, you need to concentrate on shoot through fault. Shoot through fault in the sense if the temperature of the electric drive is beyond the normal operating value, definitely the ambient temperature, we call it as ambient temperature. If it is beyond that ambient temperature, definitely the winding will be short circuited. Once the winding will be short circuited, in induction motor there is no winding isolation. It is a common three-phase winding. It is a distributed. So then the motor will be malfunction. It will be damaged. They addressed this issue in 2012 in that area when they are going with the extended driving operations about 200 kilometers, and this shoot through fault is creating problem. There is no problem with respect to, I'm talking about Tesla. Now Nissan as well as Tata Motors, they are already using this induction motor only, but they have done their some remedial measures and how to overcome these shoot through fault and how to give the maximum extended driving operations for the customer. So these I will tell you. First, I am introducing what is the shoot through fault and how we need to overcome this shoot through fault. Okay, for any electrical drive, there are only two factors. One is the battery charging capacity. Another one is the distance between the stops. Maybe if you started here and then again, if you started from Guntur
Sir,
and then you may reach
sir,
to the
1 minute, sir.
VVIT, it is around 20 kilometers. So for these,
Sir, sorry for the interruption, sir. So your PPT is not sharing.
my PPT, actually I am not moving any, just I am explaining now.
Okay, sir.
Is it PPT, this control of switch reluctance motor, it is coming now?
No, sir.
Hello?
Sir, your email is visible, sir.
Images are okay? Yeah, I'm giving just introduction, then after that I will go. Is it right?
Okay, sir. Okay, sir. Okay, sir.
As of now,
Thank
I
you,
didn't move any PPT. Just I
Okay,
am giving some introduction to the participants why we need to go for this switch reluctance motor. What is the significance of switch reluctance motor? Why we need to why we need to study this switch reluctance motor, especially for electric drive operation, electric vehicle operation, hybrid electric vehicle operation. Is it okay?
Okay, sir.
Okay, can I proceed now?
Yes, sir.
Okay, thank you. So sorry, because when we are discussing about the shoot through fault, there are mainly two factors. One is the battery charging, how we need to charge the battery. What are the different types of sources we need to start charge the battery. The second one is how to find the motor, propulsion motor. What are the different types of motors we need to use? And these motors, it depends upon the distance, how much distance you are traveling, what is the range of your travel. So, as I already introduced the shoot through fault, if shoot through fault will occur, the motor winding entirely will be damaged. But as in this switch reluctance motor, in case of switch reluctance motor, the windings are isolated. These windings are isolated, and if any shoot through fault will occur, that particular
Sir, you are in mute, sir.
May I audible?
Yes, sir.
Okay.
Sir, your voice is audible, sir.
Okay, thank you. Because why I'm just introducing the SRM motor. Why we need to go for SRM motor, and then I will finish it. Is it okay? Hello. Hello.
Yes, sir. Yes, sir.
Okay. Okay. So as we know that the switch reluctance motor has the shoot through fault. If any shoot through fault will occur, the remaining windings will be used, and then the drive electric motor.
Sir, 1 minute, sir. Sorry for disturbing you, sir. Chandrasekhar, sir. Can you share your screen once again, sir? Sir, am I audible, sir? Chandrasekhar, sir?
Yeah, you are audible, sir. Is there any problem in my screen sharing?
Sir. Yes, sir. Yes, sir. Your voice is clear, sir. Some problem with the screen sharing, sir. If possible, please share once again, sir.
1 minute. Is it okay now? Sir, my screen is visible now?
1 minute, sir. Sir. Your email, your Gmail is appearing, sir.
It shows one file, sir, only one attachment.
Okay.
Hello, is screen is visible or not?
Sir, no, sir. Hello,
1
sir.
minute, sir. 1 minute. 1 minute.
1 minute.
Is it okay, sir, now? Hello?
Yes, sir. Yes, sir. Yes, sir.
Now okay, sir.
Yes, sir.
Now
Continue.
okay? Okay?
Control of
Yes,
switch
sir. Yes,
elections
sir.
model.
Yes, sir.
Okay, sir.
Okay, it is now
Thank
control
you,
of
sir.
switcher. Okay. So I think, sorry, thank you for interrupting me and now coming to the my presentation. Thank you. Then why we need to go for the switcher reluctance motor? So as you know that these windings like a 6x4 or 8x6 or 4x2, these type of conventional configuration of rotor as well as stator is there. So I am working on 6x4 or 8x4. Maybe I will clarify why we need to go with 8x6 or 6x4 or 4x2. Because everybody, because once we will teach that, sir, what is the, if any student will ask, sir, why we need to go for only 8x6? Why not it is 6x4? Or why not it is 4x2? So if it is a 4x2, if you take the 4x2, it means 4 stator poles and 2 rotor teeth. In switch reluctance motor, we don't have any winding on the rotor, only the stator has a windings, the stator winding, and then we are switching the one winding, after that another winding, excitation of one winding, another winding. So as the rotor has no winding, so then it can be suitable for to run up to about 10,000 rpm also. This is one of the advantage of switch reluctance motor. The torque by weight ratio is also less for this switch reluctance motor. The volume of this switch reluctance motor is also less compared to the conventional motors. And only the problem is it has a torque ripple. And another problem is how to sense the initial position of the rotor and initial position of the rotor teeth. The sensing, once if you hold the rotor and then it is not possible, where is the initial teeth, this is not possible. So now we need to do with some sensorless control technique the identification of initial rotor teeth. So once the rotor and stator both are aligned together, so then the rotor pole is coincidence, to start the excitation of stator pole. So if the rotor is sensing coincidence, so then this is the aligned position. So unaligned position, the stator pole axis is along with the interpole axis of the rotor, which is called as an unaligned position. So when the unaligned position has the maximum reluctance, if the aligned position has a minimum reluctance, so this switch reluctance motor is operated with the principle of reluctance principle. So as you know that reluctance is equal to 1 by mu L by A. So as the mu is the permeability, is inversely proportional to the reluctance. And also the max flux linkages or flux is equal to magnetomotive force by reluctance. As the reluctance is low, the flux linkages will be more. So if it is aligned position, it will use the maximum flux linkages. If it is unaligned position, so the maximum reluctance will be there, but the flux linkages will be minimum. The flux will be minimum here. So and then intermediate position, and during the rotation of the rotor, the reluctance of the motor varies from minimum to the maximum. And these are the general basic expressions of the stator, and the torque equation is also like this I mentioned. If you see for motoring action and also generator action, so both motoring action as well as generator action, if you see here, this is the theta naught. So theta naught here is, this is the theta naught. Okay. And theta 1 and theta 2. So I mentioned here the theta 1 and theta 2 also. The initial angle here, the theta 1 and theta 2 are like this, and theta 3 is like this. So the inductance is also changes, because as you know, inductance L is equal to N square by S. S is the reluctance. So as the reluctance changes, the inductance is also changes. So for motoring action, it is operated in the positive slope, and for the braking action, it is operated in the negative slope. So these things are, this is the basic fundamental. And what I propose, because now see, electric vehicles, like electric vehicle can be extended up to 200 kilometers or 300 kilometers or above that also. This plug-in hybrid electric vehicles like e-rickshaws, and these e-rickshaws also now they are extended their operation. Initially the e-rickshaws operated is up to 50 miles only, 50 miles, not kilometer, 50 miles, 50 miles. But now the research is going on how to extend these plug-in hybrid electric vehicles for extended driving operation. So in this case, what I have done is I proposed the different driving modes of operation with this proposed diagram. This is my proposed integrated topology. I consider here the PV and some battery bank is also there here. And this is the asymmetrical converter topology. This particular is the asymmetrical converter topology. And this is the front end converter. So this is the front end converter. And here, if you see, this is the power flow and how I am operating this electric vehicle in different modes, because you know that the gear 1 position, gear 2 position, gear 3 and 5 gears will be there, and reverse gear is also there in our conventional cars or conventional vehicle system. But what I did is, so this is my proposal. I already worked on this particular area with the SRM motor, with the sensorless control. Anyway, I am not talking about the how I am controlling the sensorless. That also I will let you know. I will introduce that also. See here, one is the battery bank, another one is the PV system. So for this motoring operation, so here there are majorly two types of modes. One is the motoring mode, another one is the charging mode. And here the three switches are there. Switch in the sense relay here. So here, so battery mode, and this is the charging mode. So both electric PV as well as charging 5. So here I have proposed the 6 modes. One is PV alone driving mode, and battery alone driving mode, hybrid driving mode, PV driving mode, PV driving, that is charging, and battery charging by external power source mode, and battery charging by PV. So these are the modes I proposed, and this is my front end converter as well as asymmetrical motor, and these are the windings of my switch reluctance motor. If you see the PV alone driving mode, so when these J1 and J2, so here I already mentioned what is the J1. So this is switch J1 and switch J2 and switch J3. These are the switches here. You can see in this particular diagram, switch J1, J2.
Excuse me, sir. Chandrasekhar,
Yes.
sir.
Yes.
Sir, please change your slide, sir. Only first slide, control of switch reluctance motor slide is visible, sir.
So now I already changed it, sir.
Okay, sir. Thank you, sir. Okay, sir.
Is it coming now?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
This is proposed.
Sorry for the interruption, sir.
Is it coming now or not?
Sir.
Hello?
Okay, sir. Okay, sir. Thank you, sir.
Sir, is it
now it is
visible
okay,
or
sir.
not, sir? Please let me know.
It is visible, sir.
So what is visible? Tell me. This is circuit.
Proposed integrated topology for PHEVs.
Plug-in hybrid electric vehicles.
Yes, plug-in hybrid.
Now, if it is visible, next slide I move now. Hello?
Okay, sir. Now it is okay, sir.
Power flow chart in 2 modes.
No, sir. Only the previous one, sir. Proposed integrated topology for PHEV.
Now
Okay, sir. Now.
see?
Yes, sir. Yes, sir. Another screen, sir.
Now?
Power flow chart, sir.
Now?
Yes, sir. Yes, sir.
Don't know when I am going.
Now the screen is moving, sir.
Hello?
Yes, sir. Sir.
It is moving now. Slides are moving.
Yes, sir. Moving, sir. It is moving, sir.
Only when
Excuse me, sir. Make it in slide mode, sir, so that it will be visible.
I already, when I make it as a slide mode, it is not moving. Slides are not moving.
Okay.
Is it now? If you can tell me now, it is visible?
Yes, sir. Power flow chart in 2 motors.
Oh, no. I am in slide number 6 now.
I think it is slide number 5. Yes, sir. Now you are in 6, I think.
Yeah. Now it is visible or not? You can tell me now.
Yes, sir. Visible, sir. It is slide number 6.
Now I move to slide number 7. Control scheme for proposed integrated topology. Hello?
Sir. It is only 6, sir. It shows only 6 slide.
better. I think I will. Don't know what is.
Control scheme for the proposed. Yes, it is moving, sir.
Okay. So actually, when I am going with the slide slow, it is not. It is not coming. I don't know why it is not coming.
Okay, sir.
Okay. This power flow is coming now. Power flow chart.
Yes, sir.
Hello.
Power flow chart in two modes.
Yeah. Actually, what
Modes
I
of operation
propose.
with respect. Yes.
Yeah. What I propose here in this particular diagram, this proposed integrated topology for PH plug-in hybrid electric vehicle. So this is the asymmetrical converter topology. So this particular is the asymmetrical topology, and this is the front-end converter I have developed here. In this front-end converter, there are three relays are there. The first relay is J1, the second relay is J2, and these J1 and J2 are the batteries. Here the battery 1 and battery 2, and J3 is the PV panel here. J3 is the PV panel here. Okay, and if you come to this diagram, so here J1, J2, J3. For my understanding, or for your understanding purpose, I mentioned here J1, J2, J3. When the PV alone driving mode, okay, when the PV alone driving mode, what I am doing is when J1 and J2 are open, okay, J1 and J2 are open, and only the J3 is connected. It means J1 and J2 are open in the sense these batteries are not connected, only J3 is closed. So when the J3 is closed and this PV is connected to the circuit now. Okay, I think my slides are visible now. Please, is it okay?
Yes, sir.
Hello?
Visible, sir. Yes,
Visible,
sir.
and then
Visible,
you
sir.
are getting my slides. I think it is moving, right?
Yes, sir. Visible, sir.
Yeah. Please, thank you. Okay, so J1 and J2 are open position in the sense the batteries are not connected. These batteries are not connected, and the only PV is connected to the converter, and then the drive is possible. That is PV alone driving mode. Battery alone driving mode in the sense this J1 and J2 is connected, and this PV is not connected there. Hybrid mode in the sense all the three, like batteries as well as PV is also connected here, and PV driven charging mode. So where I required this PV driven charging mode. So when J1, J2 are closed and PV drives the SRM motor. So if you see this, and also battery charging by external power source. So this from this external source, this is charging file. So this is nothing but as when you charge the charging plug is there, and then you need to charge it. So when J1, J2 are closed and J3 is open, so then the battery packs are charged through an external source, and battery charges by the
Sir, your mic is muted, sir.
Hello, sir. Chandrasekhar, sir.
Ah,
Please unmute your mic, sir.
sir, I already unmuted, sir. Can see?
Okay, okay, sir. Okay, sir.
Is it visible? Audible?
Yes, sir. Audible, sir. Please continue, sir.
Okay. So this is my starting in the starting condition, both PV as well as battery charging together because it required high starting. So that's why what I have done is in the hybrid condition when PV as well as battery, it has both. I think like in the sense hybrid mode, high starting will also possible here. At the low running, if you are started with the low running speed of operation, so in the low running period, only battery is working. So then it will go with the battery alone driving mode, second mode. And in the acceleration, when it has some slope is there, so in the acceleration, some height is you are going. If you are going with the hill station, so now you need some acceleration. So there PV and battery working together. Same, whatever we have started here, the first starting condition, in the third also, PV and battery working together. So when you want to go with the high speed, when the motor, when the vehicle is started and then it is going with a certain speed. So I have given some speed also, speed limitations also. So when I'm doing the simulation in the controller, I have given the in the starting condition 0 speed. When it is a low speed condition, it is going up to 60 kilometers per hour. And in the acceleration, even if it is a 10 kilometers per hour, also the acceleration mode. So during that time also, what I have did is both PV as well as battery together working. And in the high speed running condition, the high speed in the sense if the above 65 kilometers, above 60 to 100 kilometers, I consider as a high speed range, because it is not possible only one speed. I will go with only 60 kilometers per hour. Somebody will go 80 kilometers. Somebody will go up to 100 kilometers also. If it is at the high speed region, I classify it as a 60 to 100 kilometers. So during this particular mode, only PV is working. That is my first mode of operation. And coming to the deacceleration, this is the braking also. In the braking condition, so now already your vehicle is moving, and whatever the energy, you know that the energy is fed back to the source with the braking operation. So during that condition, the battery is charging. So here battery is charging during the braking condition as well as when you connect some external source. So this is I have proposed in my project, and I already started working on this. And what type of control scheme for the proposed integrated topology? As I already informed you, it is very difficult to identify the initial position of the rotor, because I already told you the aligned position and unaligned position. So how to find out the aligned position? So then what I am doing is, so this is the control scheme I proposed for my topology. I proposed this, that is the speed of the motor is equal to 2 pi by t, that is the damping time, 1 by PR minus 1 by PS. So PR is the number of poles in the rotor, and number of poles in the sense number of teeth, okay, and PS in the sense number of poles in the stator. I hope my slides are moving now. And what I did is, so in the sensorless control, this is the sensorless control scheme I proposed. By stator flux linkages. For example, I don't know where is the initial position of the rotor. Just I excited phase A. For example, if you go with the phase A, I excited. When the phase A is excited, then if it is already the rotor teeth is also aligned with the stator, so then there is no movement will be coming, because it is already aligned. Even though if I started giving phase A. There are two conditions here. There is no movement on the rotor. If there is no movement on the rotor in the sense, for example, you are giving excitation to stator A. So stator A is already aligned. The rotor teeth is also aligned, so that it is not, there is no movement in the rotor. So in that case, what you need to go with, you need to start the next phase of the stator for excitation. So if you start the next phase, so then the rotor will slowly align to the next phase. So like this, when it is aligned, so then the flux linkages is coming to reaches. I am giving the reference flux. So how I am calculating the reference flux? Based on the stator current and flux linkages, I calculate the reference flux. And once I am reaching the reference flux, then it will go to the next phase winding excitation. And for these reference flux linkages, I have calculated based on my mathematical analysis. And these mathematical analysis are implemented in the MATLAB. Okay, and like lookup table, these flux linkages and reference flux are calculated by lookup table, and this is going to the phase computation. When the stator phase A is reaches to the maximum flux linkages, and immediately it will go for the stator B. If the stator B flux linkages is reaches to the maximum level, next it will go to the stator phase C. So like this, I have analyzed based on the lookup table analysis and also based on the flux calculations. Okay, the flux calculation, this is the formula I have used, and this is the sensorless control scheme I have proposed. And these are the initial observations I observed in the MATLAB simulation. stator flux linkage of SRM motor, stator flux currents of the SRM motor, and speed error. This is the conventional as I compared with the with sensor what we are doing, without sensor, the sensorless control what we are doing. So this is I have done. So this is the proposed sensor controllers C. So here if you go with the phase A flux linkages, phase B flux linkages, phase C flux linkages, and phase D flux linkages. So if you see the phase D, this is the phase D, and the maximum flux linkages is 0.42. This is what the reference flux linkage value is 0.42. And once the 0.42 will reach, then because 6 by 4, why I am considering here phase A, phase B, phase C, phase D is the rotor has 4 teeth and stator has 6 poles, okay, 6 stator winding. So if I go with the phase D, one so once the phase A, again it is started excitation, and once the phase A flux linkages will reaches the reference flux linkages. Reference flux linkage is 0.4, I can 42. Next one is phase B will start. So again in the phase B, again next phase C will start here. And then next phase D. So this is the sensorless control scheme we proposed. And then we already dumped this program to the SRM motor and our controller also. So first part, I explained how I am doing the charging of motoring as well as motoring mode as well as charging mode. And second part is how I am controlling the SRM motor through sensorless control. Okay, this is what I have done. And now I already executed this SRM motor with a plug-in hybrid electric vehicle. So now I have made an MOU with the Speedway. They are already developing in Punjab. They are already developing the electric motor. This NIT Delhi. So we are now going with the developing of this particular. What I have done in my lab, hardware setup, and now I am executing with the Speedway. They are already developing their electric vehicles now. So with this control technology, so now I am transferring my technology to them. And this is the this is one way of controlling of SRM motor. So I think you already aware about this. SRM motor has some initial position. How we need to identify the initial position of the SRM rotor teeth. So because of this problem, majority of SRM motors are not utilizing for electric drive electrical vehicle application. So with this, what they are going again, this Tesla has also now made as a flux reversal mission. So they are called as a, Tesla is not named as a flux reversal motor. They name it as a internal, okay, they consider as a permanent magnetic internal synchronous reluctance motor. Internal synchronous reluctance motor they are using. They have changed that name, like as a this flux reversal motor, they changed as a some modification in the motor configuration, and then they use it as a internal synchronous reluctance motor. They are using this Tesla. But now, for our understanding purpose, I am explaining the flux reversal motor. This is also one of the motor which is now used for the electric drive electric vehicle propulsion system. So this is very simple construction. Only the problem in this one is construction, but the working principle is very simple. As we know the Faraday's laws of electromagnetic induction, then it will be very easy also. So this is the EMF equation. The EMF equation. So what are the parameters here? And then I already explained. And this is the torque equation of SRM motor. Just I have used the comparison of different motors which are used for the electric vehicle. One is the switched reluctance motor, another one is the BLDC motor, and flux reversal motor. So with the flux variation and magneto MMF variation and the energy conversion loop, and okay, and then for rotor inertia I have considered here. So these are the different comparison. And if you see the principle of operation of FRM motor, so in the permanent magnets, see this. I hope my slides are visible, right? Hello?
Yes, yes, sir. Yes, sir.
I am requesting the audience, if you have any doubts in between also, you can please interrupt me, because it is not a one-way communication. I will prefer the two-way. At any time, if you have any doubts, please let me interrupt, and then we will go for the discussion. I am not waiting for the end of my presentation. I need to discuss. If I am teaching, whether you are following or not, I don't know. Especially with the online mode, I think it is very difficult whether you are coping with my presentation or not. So if you have any doubts, please immediately disturb me. Then I will clarify it also. Okay, this is the basic 2x3 configuration of flux reversal motor. As I already addressed one participant is asking, sir, why you need to consider only 6x4, or why you need to consider only 8x6 in a SRM motor? Why not it is a 4x2? If you consider 4x2, so the step angle is the important. The step angle will be 90 degrees, 4x2. If you consider 6x4, 6 poles or 6 stator poles and 4 rotor teeth, the step angle is in between 15 degrees, or it is in between 30 to 60 degrees. If you consider 8x6, the step angle is, we are coming reducing, the step angle is 10 degrees only. So that's why the optimal design of any SRM motor is 8x6 or 6x4 only that using. Here, in case of FRM motor, so this is the stator, and
Sir, your mic is muted, sir.
yes. Okay. So see, this is the configuration of FRM motor, flux reversal motor. The stator, permanent magnets here. These permanent magnets are placed on the pole show. Okay, so this pole show, again here, North Pole and South Pole. In the bottom also, like North Pole and South Pole, we are moving. And this is the rotor. Rotor here. Rotor also, there is no winding. It's only teeth, I think. Rotor teeth are there. See, this is the initial position. So half of the North Pole, and coming to the first case A here, its operation depends upon the 4 cases here. The first case A, it is in between, the rotor teeth is half of the North Pole and half of the South Pole. So then there is no flux linkages. So then during that particular position, the flux linkages will be 0. Then if the rotor teeth is moving at a 30 degrees anti-clockwise direction, if rotor teeth is moving to the 30 degrees of anti-clockwise direction, so you can see here, this rotor teeth is completely aligned with the North Pole of the, okay. So then what will happen here, in the South Pole, this is the direction of the flux, and in the North Pole also direction of flux. So then the rate of change of flux linkage is possible. In the bottom also you can see like same, the bottom also. So then it will start, some flux will be coming here. And again, what I am doing is, so from case A to case B, 30 degrees, and case B to case C, again I am rotating anti-clockwise direction. So in this case also, the symmetry is existing between permanent magnets on the pole and rotor axis here. So then there is no rate of change of flux linkage in case C also. In case C, again 30 degrees anti-clockwise direction. So now see, the South Pole in both the cases, it is aligned. So when you are rotating the rotor teeth, whenever the rotor teeth is moving, initial movement by an anti-clockwise direction at 30 degrees or 60 degrees. If you require the more step angle, you go for 60 degrees. Reduce it by considering this 4 by 6 or 8 by 6, okay, or 2 by 3 configuration. I consider here 2 by 3. 2 by 3 in the sense 2 stator and 3 rotor teeth here. Okay, and I hope you understand, you got my point, how these flux linkages are existing in the FRM motor, flux reversal motor. So in the first case, the rotor teeth is symmetrical between the north pole as well as south pole. There is no flux linkages. Okay, the rate of change of flux linkage will be 0. Here I already mentioned here. In the second case, when the rotor is moved by 30 degrees anti-clockwise direction, so this rotor teeth is symmetrical with the north pole in the both bottom as well as top here. So now the stator flux and rotor flux now are existing here. The rate of change of flux linkage are existing here. Okay, then in this case, it will be like this only. So now when from phase B to phase C, from case B to case C, again I move to the rotor by 30 degrees. So now here again, whatever the case A, in case B is also existing here. See? And after the case B, again I move to 30 degrees. So now this is the case C. So this configuration, the Tesla has already started, and then they now the Tesla motors are running with this. They're not name it as a flux reversal motor. They name it as a internal permanent magnetic synchronous reluctance motor. They name it as a different terminology, internal permanent magnetic synchronous motor. So these are the internal permanent magnets are placed in the pole shoe, and these pole shoe also now this ambient temperature heating is also not a problem in this arrangement. And this is why you are going with FRM motor. Why not SRM motor? Why not BLDC motor? Why not this doubly silented synchronous motors? So these are in a SRM motor, in switch reluctance motor, this magnetomotive force and phase flux is a unidirectional. Okay, it's unidirectional. And in doubly silent permanent magnetic motor is also like bidirectional, but the negative flux is not possible here. BLDC motor, it is possible. It is a trapezoidal operation. BLDC motor is also possible, but when it comes to the FRM motor is, see, you can see the change of from positive to negative. It is possible when compared to the BLDC motor. So this is the comparison between FRM motor and doubly silented permanent magnetic machine and brushless DC motor and FRM motor using the magnetic flux MMF diagrams. And I have already done this FRM motor in the ANSYS. I am using the ANSYS software, Maxwell's equations. I am using this in the ANSYS platform. I have developed this like 6 by 8, 6 stator and 8 teeth here. So these are my parameters what I consider for stator as well as rotor. And also here I consider the magnets are cadmium cobalt 24 magnet I consider. So if I will talk the permanent magnet again, it may go half an hour discussion. So why you consider only cadmium cobalt? So there are Alnico, Alcomex, cadmium cobalt, neodymium. So neodymium is one of the best permanent magnet. The Curie point temperature is also good for really. Okay, this cadmium cobalt will also give us the Curie point temperature is very good, and maximum flux linkage is also possible. I consider here first, before going to the hardware setup, I was done this analysis in the ANSYS software. So this is my, sir, is my presentation is visible? Hello?
Yes, sir. Yes, sir. Visible, sir.
Conventional 6 by 8 FRM motor is visible now. Hello?
Sir, hello.
Yeah. Is it visible, sir?
No, sir. Change the slide, sir.
Okay.
Table 1 materials used in FRM is visible, sir. Yes, sir. Conventional FRM is usable, sir.
Okay,
Continue,
okay,
sir.
okay.
Continue, sir.
Okay. So the flux linkages of conventional FRM motor and the induced voltages of the conventional FRM motor, and here this is the cogging torque. This is one of the major factor when you go with the special electric motors. This cogging torque is one of the problem. Cogging. So how to minimize this cogging? How to neutralize this cogging? It's not possible to neutralize, but we need to minimize itself. So for this case, what I have done is I consider the different rotor structures to reduce the cogging. Because what I have, as from the literature, there are three types of rotors are possible. One is rotor pole pairing, another one is rotor pole champering, another one is the rotor pole skewing. So these are the three rotor configurations which are available for FRM motor, flux reversal motor. So in pole pairing, if you see the observe here in the pole pairing, rotor pole pairing, the rotor pole width, one pole has this is the different pole widths I consider here. Okay, in rotor pole pairing and rotor pole champering. So this is also another technique. So why I am using these techniques is to minimize the cogging torque. Okay, cogging, sometimes we call it as a ripple torque or cogging torque. Okay, so again here rotor skewing technology, skewing. So the combined technique. So this is the earlier is the conventional 6x8 FRM motor, and now what I have done is first I tested with these two techniques, rotor pole pairing and rotor pole champering. Then what is the cogging torque? And again I tested in the simulation rotor pole champering and rotor skewing, rotor pole skewing. Then again what is the cogging torque? Then what I have done is after combining all these techniques, I am getting less cogging torque. And that is the combined technique. This is the combined technique. And with this combined technique, I again designed the FRM motor. And these are the flux linkages. This is the rotor pole skewing technique when I done in the ANSYS software. So these are the ANSYS waveform images. And this is the modified flux reversal motor. The flux density, see here, the flux density areas and how it is, the variation of the fluxes also I consider here. You can see here for this particular, for modified technique. So I have seen, you can see here in my comparison table also, different parameters I have considered: flux linkages, induced voltage, torque, and cogging torque. Cogging torque peak to peak I consider here. For rotor pole pairing, the flux linkage will be 0.432 wafers. And for rotor pole skewing, 0.269. And the conventional is 0.472. And the modified in the sense I introduced all rotor pole pairing, rotor champering, and rotor skewing. So then the modified method or modified model, I got these are the flux linkages, less flux linkage. Compared to the conventional, I got less value, but the cogging torque is reduced here, 0.7052. This is reduced here. And the torque is also, the amount of the average torque is 18.527 Newton meters I'm getting. The major thing is, this is the major problem. The cogging torque we need to reduce. So in the modified method, I got the less cogging torque here. So this is the one method which is also used for the electric vehicle movement, propulsion of electric vehicle. And coming to the another one is, so now people are already working aware about this linear induction motor. Sir, how much time I have? Hello? Hello?
Sir, you can
Hello?
continue, sir, up to 11, and sir, up to 11:30.
Okay, thank you. This linear induction motor, the linear induction motor is also similar to the synchronous motor, like induction motor. So this is the cylindrical mission, like what we have, like induction motor. The cylindrical mission is an induction motor. The three-phase, phase A, phase B, phase C, and the stator and rotor and air gap is also existing here. So once you cut this one end of this rotor, this induction motor, and then put it in a linear fashion. So the same, the cylindrical mission, and this is the linear mission. So the same phase A, phase B, phase C, and again phase A. So this A and A dash axis, like A and A dash axis, and this is the air gap here, okay, and the stator and rotor here. So this is the linear motor. I developed the linear induction motor. I have implemented this linear induction motor in hardware model in my lab. I will share my experiences, what I have done. What is the principle of linear induction motor? So linear induction motor, by cutting one way of the rotor, cage rotor or wound rotor, the stator become as a primary and rotor become as a secondary, like a transformer. And the primary of an induction motor, the linear induction motor, is excited by a balanced three-phase supply. So the primary is excited by the balanced three-phase supply. Instead of the rotating magnetic field, here the traveling flux is induced. If you know induction motor, the rotating magnetic field RMF is equal to 1.5 times of maximum flux linkage. But here, if you put it as a linear fashion, the traveling flux is induced in the primary instead of the rotating. The electrical currents is induced in the aluminum conductors due to the relative motion between the traveling flux and the conductor. So then this induced current interacts with the traveling fluxes and then thereby produces the force on it. And this is the design of linear induction motor.
Sir, voice is not audible, sir. Chandrasekhar, sir.
Yeah. Is it okay, sir, now?
Okay, sir. Sir, unmute your mic, sir. Sir.
Somebody is calling with this app, so that's why it is happening.
Okay, sir. Okay, sir.
While using this app, somebody is calling. So because of that, I am getting interruption. Okay. So the traveling flux is there. Instead of the rotating magnetic field in asymmetrical motor, the traveling flux is produced here. And this traveling flux will interact with the rotor conductors and thereby the torque will be producing here. This is the basic principle of linear induction motor. And this is the design of linear induction motor. And this is the double-sided linear induction motor. And the primary winding here and the secondary. This primary is a just as this is the stationary one, and this is the secondary. Okay, and this it is moving now. This can be used for magnetic levitation application. The linear induction motor can be used for the magnetic levitation application, especially for magnetic electric traction purpose. Also, we are using this. I have considered this is the equivalent circuit of linear induction motor, and these are the equivalent circuit parameters. And this is the linear velocity of traveling wave, how much stator voltage and how much rotor voltage, and what is the speed of this. So I think you will address one problem. You have one doubt, sir, when you are cutting the induction motor in a linear fashion, then what about the traveling flux? Definitely the end effect and edge effect will also be existing. So how to neutralize this end effect and edge effect? That is also another set of research. So this is the laminations I have considered. The lamination size, I designed the laminations, and these are the laminations after purchasing the CRGO material, silicon steel laminations. Based on these dimensions, we in the lab, I think we have cutting these laminations, and I have made the complete laminations with a core. I think this is the laminated core, and this is my winding arrangement. After this, I have done the winding arrangement. The number of slots I consider 12, and number of poles I consider 2. Number of phases is 3 phase, and the number of slots for pole for phase is 1, and pole pitch is 6, and slot angle is 30 degrees. Full pitch winding, the coil span is 180 degrees, and also this coil span is 6 slots I am considering. And this is the winding arrangement for single layer winding configuration. So this R phase, Y phase, and B phase. So based on these winding arrangement, I have done this is the winding diagram, And after putting this is my complete setup. This is primary setup. So this is my stator. So see here that these three coils, coil A, coil B, and coil C. And again, coil A, coil B, coil, because it is a two pole. This is one pole and this is another pole, two pole mission. Because I considered here number of poles is 2 and number of slots is 12 slot. So I developed this linear induction motor in the lab. This is the mild steel table and the primary winding and primary slots, and this is the primary setup I have done. This is the winding diagram, and the primary winding setup is the single layer winding. And see the secondary, what I have considered the secondary is the aluminum bar, and I have attached some wheels on the aluminum. This is nothing but as a secondary, the design of the secondary rail. And this is the static magnetic field distribution. I am giving the DC excitation to the stator winding. So once I am giving the DC excitation to the stator winding, so how the variation of air gap flux density versus the mean length of the phase A for the different values. I considered here the phase A current is 2.5 amperes, 3 amperes, and 3.5 amperes. For different excitations, 2.5 and 3 and 3.5, this is the wave I am getting, three phase. Instead of the sinusoidal, it is getting as a square wave or quasi square wave I am getting here. And also this is the variation of area flux linkages, the mean length, output currents. This is my for different values of the current, and this is also I'm getting like this. See how I measured. The measuring of flux can be done by Gauss meter. The measurement of magnetic flux, I connected here Gauss meter here, and then I measured these values. And these are the for 2.5 amperes of excitation and 2.08 volts. Maybe the voltage 2.5 for phase A, phase B, phase C. I tabulated these values, and then after tabulating this, I found these are the variations. After drawing these values, I'm getting the three-phase waveforms. When it is a 3 amperes and when it is a 3.5 amperes. So here see for 3 amperes the blue 2.5 is the blue line, red line, and these are the for each excitation. So I'm getting the sinusoidal voltages here, three-phase voltage. And also how to find out this measurement of linear force by thrust, I think. Like as a linear force is nothing but as a thrust. So when you excite the primary winding, and I'm putting the primary and secondary can be insulated, but this is the wood is the insulating material. Okay, so when you excite the primary winding, the magnetic field, traveling magnetic field or traveling flux is created, and because of the traveling flux, this secondary rail is moving. And I consider the variation of the secondary velocity with respect to input current, and thrust versus speed and thrust characteristics. These are the thrust versus speed characteristics. I have calculated for each excitation, and then I tabulated the results through MATLAB coding. And this is my complete setup. See, this is the primary excitation. This is the insulating material I used, and this is my secondary, and it is moving like this. So, and these are the permanent magnets and design specifications what I have considered. So the rated voltage, rated frequency, number of poles, number of phases, synchronous velocity, secondary rotor velocity. So these are my motor parameters for the design consideration. In the similar fashion, linear induction motor, like linear synchronous motor is also there. Now this linear synchronous motor is also using for the electric vehicle propulsion system. In the similar fashion, the flux linkages, okay, the force equation and the stator voltage equation, and the no load RMS voltage, how much you are getting the no load voltage. And these are some mathematical calculations. And just I have compared with the linear induction motor with the linear permanent synchronous motor. This is the comparison. And the main problems what I identified, the thrust ripple generated due to the various reasons, like distribution of the primary flux linkage distribution, and reluctance forces and cogging forces. There is a disturbance of the positioning of the, and linear induction motor losses is also I considered. And the main research field, what I have considered, reduction of the cogging force, controlling with high speed, and minimizing of this end effect and edge effect also I have considered. So the objective is to develop a linear permanent synchronous motor using ANSYS software to minimize the cogging forces and increase the thrust. And thrust ripper of linear permanent magnetic motor, permanent synchronous motor, is a significant drawbacks. And then high thrust we have done. So the cogging force, how we need to reduce the cogging force. So cogging force, what is the interaction here? And the techniques for reduction of the cogging force. So proper pole and slot combination selection and semi-closed slot design, suitable armature length of selection, magnetic length adjustment, magnets or slot screwing, air gap length variation, proper teeth edge chamfering. So these next thing I have considered. These are the reduction of cogging forces. LCM of number of poles in the and number of slots by number of poles. This is I considered. The cogging factor K. How we need to consider the cogging factor? The LCM of number of poles and number of slots. And this is what I have done. So after doing this, the LCM NP by NS is 4 by 6, 6 by 9, 8 by 12, 9, 8 by 9, and 8 by 15. And this is the cogging factor. And this is the cogging factor. After this is the combination. Number of poles is 4 and slots is also 6. And for this case, the cogging factor is 3. The design of 8 pole and 9 slots, linear permanent magnetic synchronous motor. So you see here, these are the 8 poles and 9 slots here. I consider here the ANSYS software, and these are the mission parameters I consider: the pole pitch and slot winding, slot width and slot depth. These are the, when I am doing the ANSYS model, so these values I consider. And this is the input currents given to the permanent linear permanent magnetic synchronous motor. And these are the induced voltages of permanent synchronous motor. See here, the linear induced voltages are not clear here. Okay, so now what I have done is, this is the flux distribution. See here, the flux distribution of each phase and also each slot here. Okay, and then magnetic field lines. This is the magnetic field lines in the ANSYS software. We captured this. And this is the cogging force for 8 by 9 design. This cogging force is also like it is coming down here in this particular, because see here, up to this it is existing, and suddenly some dip is existing here because of this particular dip. So this output, the induced current in one phase is coming like this. And now again the thrust is also we calculated. The thrust value is increasing linearly. Somebody is calling and then it is disconnected. My voice is disconnected now. No, okay. And this is the cogging force. You can observe the 8 by, yes. Thrust value. And this is about the motors. And coming to the second part, this is second part is electric vehicle market in place of simulations. So electrical market, what is there? This is the market size and growth of EV industry for different countries. Like China is number 1 in electric vehicle manufacturing, and Europe and the United States and Germany, California, France. This is the scenario for 2001 to 2030, the global electric vehicle market was valued for like this. And the market size and growth of EV industry with like battery electric vehicle and plug-in hybrid electric vehicle. So now the plug-in hybrid electric vehicle is also now grooming. So now, as of now, the battery electric vehicles are moving. Okay. And the countries with highest EV market penetration, as per the graph mentioned in the previous slides, so the China and India and USA and Norway, these are the 4 countries we are using these electric vehicles as of now predominantly. The major key players and manufacturers in the EV market is Tesla, Toyota, GM, General Motors, Volkswagen, BMW, Ford, and Kia and Renault. So these are the main suppliers they are manufacturing. And the sales trends and consumer attributes towards the EV. So how the Indian scenario, China scenario, and United States and Norway scenario. So like this, the India has reached around like this in 2020. So maybe 50,000 in 2015, but now 1,40,000 in 2020. This may be again increasing for last 5 years vehicle sales. So now in India, up to 2020, 1,40,000. I think they already do. Up to 2015, it is only 50,000. So now China is already now there are 2 billions of electric vehicles they already manufactured up to 2020. Around 4 lakhs in 2015. So again, United States and Norway, this is the model. And the types of electric vehicles like battery electric vehicle, hybrid electric vehicle, plug-in hybrid electric vehicle, fuel cell electric vehicle. So this is the general comparison of different types of EVs. So this is battery electric vehicle. This is the battery case. And now plug-in hybrid electric vehicles. So what I discussed in SRM motor like plug-in hybrid electric vehicle. This is plug-in hybrid, and then this is also hybrid electric vehicle. This is the fuel cell based techniques, I think. So the comparison. So the comparison of battery electric vehicles and plug-in hybrid electric vehicles and hybrid electric vehicles and fuel cells. The types of motor I already informed you, that is asynchronous motor, the induction motor, permanent magnetic motor, the brushless DC motor is also used. These are the 3 motors. Now they are also using internal permanent synchronous reluctance motor and switch reluctance motor also using. And these are the comparison of different types of motors used, like BLDC motor, induction motor, and permanent synchronous motor. But this all the case induction motor is best, but the only problem in induction motor is because of the shoot-through fault. And because of that particular reason, if any shoot-through fault will occur, the entire winding will be damaged. So that's why, and then it is not possible to go with a reduced speed also. And these are the some simulations I have carried. I considered my simulations. These are my simulations what we have done. Anyway, types of batteries used for EVs, like now lithium-ion and lead-acid batteries they are using. So this is about my presentation, EV market in India. Tata Motors. So in India, Tata Motors is currently leading EV manufacturing in India with a market share of 50% around. And Hyundai is also second large in EV manufacturing, and they are with a share of 25%. And MG is also now 15% share. And Tata Motor offering India having up to 312 kilometers in a single charging. 312 kilometers it is going. And all 3 companies offers EV powered by the brushless DC motors. There all these companies like Tata Motors, Hyundai, okay, and MG, they are offering with brushless DC motors only, because high efficiency and high power density and low maintenance requirements. And EV market analysis in USA. USA is Tesla and GM, and Nissan. So the GM Tesla market share is around 25%, and General Motors share is 10%, and Nissan is 5%. So now the Tesla, the driving range up to 300 miles for a single charge. With the GM is also permanent magnetic motor, induction motors. Nissan is still using with induction motor only. And in China, so in China, these are the companies BYD, So these are the Leo Auto. So these companies are manufacturing in China. So this is the China scenario in EV market analysis. And Norway also the Tesla Motors are using. And in Norway, the Tesla is 45% share, market share up to 2020. And future about EV market, the continued growth, these things will be there. I hope this is about USA market analysis, so hybrid electric vehicle and battery-driven hybrid electric vehicles. And top companies in USA is Tesla Model S and the Tesla Model 3 and Tesla Model X. These are the top companies. So this is about my presentation. If you have any queries, please. Hello? Hello? Hello?
Dear participants, if you have any discussions to discuss with the speaker, please ask them. Thank you very much, sir, on behalf of Department of EEE and VVIT for your valuable session. Thank you, sir.
Thank you, madam. Thank you, sir.
Thank you. If you have any doubts, please let me ask. Otherwise, you can reach by my email ID, Dr.O.Chandra@nitdelhi.ac.in. You can contact me and you can follow my web page also. My research updates will also be there. Can I leave now or hello?
Yes, sir. You can give, sir. Thank you. Thank you, sir. Thank you very much.
Dear participants, next session will be started at 1:30 p.m. Let us end this session. Thank you.
Hello, madam. Any feedback from?
I think they will share in WhatsApp group, sir.
Okay.